Good morning, everyone. Thank you so much for joining us for our webinar today. My name is Catherine Keeler. I'm the Executive Director of the Fiber Optic Sensing Association, otherwise known as FOSA. And we're talking today about scaling fiber optic sensing for critical energy infrastructure. We're looking at the BRUA pipeline and the future of pipeline monitoring. So today we're going to examine how distributed fiber optic sensing can be deployed at scale for complex cross-border energy projects and energy corridors. And our speakers will share insights from the award-winning BRUA project in Eastern Europe and discuss how these technologies are reshaping pipeline monitoring, risk management, and long-term infrastructure resilience. And I wanted to say thank you so much to our three speakers today. We have Dr. Wissem Sfar Zaoui from AP Sensing. He's the project management team lead. He oversees fiber optic monitoring projects across pipeline and power sectors. He holds a PhD from the University of Stuttgart, is PMP certified, and brings deep expertise in integrated photonics supported by more than 30 publications and patents. We also have Dr. Alex Joode, head of pipeline and terminals with AP Sensing. He has more than 25 years of experience spanning engineering, international sales, and marketing, and his work focuses on aligning advanced software and distributed sensing technologies with real-world needs in the energy and water industries. And also Dr. Paul Dickinson, the founder and principal of Smart Infrastructure Solutions. He is a recognized authority in materials technology, optical fiber, and distributed sensing strategy with over 35 years in the field. He's a longtime industry leader, and he continues to shape innovative infrastructure development through consulting, advisory roles, and thought leadership. And with that, thank you again for joining us today, and I will turn this over to Dr. Paul Dickinson.
Thanks, Catherine, and thanks to FOSA for the opportunity for the three of us to speak here. We're going to have a lot of fun today. We're going to try to get through three distinct parts of the presentation in about 45 minutes, and then allow plenty of time for questions and answers. So please think of your questions and answers that you'd like to receive from us as we're speaking here. I'm going to kick it off with about 15-minute discussion, just with a little bit of vision of why this is so urgent and critical right now, not just for pipelines, but for overall infrastructure, and how DFOS plays a huge role in that going forward. And then I'm going to turn it over to Alex Joode, who's going to get into technology deep dive for pipelines. And then finally, Wissem is going to come in at the end and talk in detail with the granularity about the BRUA project, which is very exciting. This was the 2025 FOSA award-winning project. With that, I'm going to see if my slides will move forward. And they do. So this is just information. You can get everything you want to know about me from that QR code. I just leave this for your needs if you want to go back to the archive and grab it later on. I'm going to move quickly here, and I want to start by saying that I'm going to show a lot of data, and the qualifier I want to provide is that there's not a lot of good data out there for some of the things I'm going to talk about, but that doesn't mean we shouldn't talk about it. I want to go through the enormous, on this slide, enormous number of miles that exist of infrastructure currently, both in the US and globally. And doing the research, these are the numbers I came up with. In the US, for example, in post-World War II boom, there's been a tremendous build out of the miles you see here in oil and gas pipelines, electrical grid, rail, bridges. I mean, we're talking over 10 million miles of infrastructure, either under the ground or above the ground. And on a global basis, so that represents about 16% of the total global infrastructure. On the right, you'll see the global infrastructure broken out just for oil and gas pipelines and for electrical grid. That's about 55 million miles. And the total, if you sum up the other parts, is about 65 million miles. So we're talking a tremendous amount of infrastructure that's out there now. The important part here is that they're starting to fail. The American Society of Civil Engineers gave the infrastructure a rating of C in their most recent report. And in this breakout here, you'll see that the design lifetime is nearing its end for much of the infrastructure that currently exists. So this is a problem. Pipelines, transmission lines, water systems, bridges, They're all starting to wear out and they're starting to fail. So this is something that with existing infrastructure, let alone new build, that we need to address going forward. In the next slide, I want to talk about what are the critical vulnerability factors as these parts of our infrastructure start to age. They're listed here. There are more, but these are the top five. Material degradation. So old materials begin breaking down. Maybe they were inappropriate materials or materials that aren't as advanced as the current materials. Older steels, they're starting to degrade. Also, the systems are being stressed more and more. They're running at their design limits, and in some cases, perhaps a little bit beyond. This is causing operating stress to occur in their along all these different facets of our infrastructure. And then there's throughput demands. You'll see that this is only increasing going forward, but we're pushing more capacity either at the limits or in some cases a little bit beyond what they were originally designed for. And let's not forget about climate and weather factors. Hopefully we can contain the climate shift that's going on right now. But the bottom line is that extreme climates have an impact on our infrastructure and in some cases accelerate degradation. And then the other issue is deferred maintenance. It costs a lot to maintain this infrastructure. We're talking infrastructure again that's 40, 50 years old in some cases. Just to show one example here, there's a $452 billion water gap alone where infrastructure needs to be replaced. I remember a statistic where on long water pipelines, sometimes 30, 40% of the water is lost. And that's terrible. So we're operating 20th century infrastructure under 21st century demands. In the next slide, oh, I went too far. In the next slide, I want to talk about the daily tolls that occur with respect to this infrastructure. And I want to focus, you're going to hear later in the talk, primarily a focus on pipelines. So that's why I'm focusing here. There are the U.S. pipeline incidents that occur, and these are the serious ones, about 1.5 to 1.7 per day. Now, these are not all the incidents that occur on a daily basis. The Common Ground Alliance reports, for example, that in the U.S. alone, there's $30 billion in excavation damage occurring annually, with about 500,000 damages, literal damages that occur every year, distinct damages. What I'm showing you here are serious FOSA incidents. FOSA incidents are classified by deaths, hospitalization, major gas releases, things that you read about in the news that are very serious. On the top right, you'll see a breakdown of what the approximate causes are for these failures of the system. And they break down into the categories you see here: third-party interference, leaks, corrosion, natural forces, and a few others. The point I want to make here, when Alex gets into the details, if you're not familiar with how DFOS technology works, is that we have the potential of positively impacting as many as 40 to 70% of incidents that occur in these categories. That's huge. So, and the cost, not only in human life, but in monetary value, you see broken down here. The cost is on the range of $25 million on median, with a range that can be as much as $500 million. So again, these numbers, they're tough to get a hold of because a lot of people don't like to report these incidents. These are FEMSA related numbers and they're just huge. The point I'm trying to make is distributed fiber optic sensing, the technology you're going to hear about today, and the monumental effort that AP Sensing undertook to show how this can be done on a large scale can impact positively these events. And let's talk now about what current monitoring technology exists for pipelines in specific here. Now, there's a lot, and it's actually working quite well in some cases. What I've broken down in this table are three types of monitoring that exist for pipelines: point sensors, aerial and ground patrols, and smart pipeline inspection gauges, otherwise the acronym is known as PIGs. The issue with these sensors, while they're critical, while they're necessary, while they play a very vital role, is they're either sparse in their ability to be everywhere on a pipeline, or they're quite comprehensive, but they're periodic in terms of when they're able to be capturing data. So none of these technologies really are giving you real-time continuous coverage of every meter. And what you're going to hear about, again, with Alex and Wissem in the near future here, that distributed fiber optic sensing fills that gap. This is not a technology that replaces these very valuable technologies. This is a technology that complements and contributes to a total tech package where you can provide then continuous, comprehensive, and real-time detection all along the corridor. And now, if that wasn't significant enough in terms of aging infrastructure, there's the AI multiplier. You can't watch the news or read LinkedIn or anything for that matter without basically hearing about AI and all the data centers that are about to be built. So again, this is data that I gathered through some electrical organizations that I'm a member of, and also through some research on the tremendous multiplier that the building of data centers is going to cause in our infrastructure builds. So AI basically is forcing our physical infrastructure growth at a scale not seen since the dawn of time when we had rural electrification passing out through rural areas in the US and globally. Just to quote a couple statistics, the data center power demand in 2025 is about 860 terawatt hours. And in 2030, there needs to be an 85% increase estimated in order to meet the energy demands of not only aging infrastructure, but data centers. What that requires is 100 gigawatts new US capacity, where half of it is data center driven, 25,000 miles of new transmission lines by 2030, and a current building rate of about 5,000 miles per year, where right now we're only building at about 400 miles per year. So this global grid expansion is going to be huge. It's going to tax existing systems. And frankly, if we don't accelerate the build of the power grid, it's not going to be able to support the aspirations of all the hyperscalers and all the other folks who want to use generative AI more and more. So we're talking 18 million kilometers by 2030. That's a 20 to 25% growth, or a $3.1 trillion investment. And then on top of that, let's not forget about renewables. Renewables need to be integrated in the system to provide additional sources of energy. And I hate to mention it, but the geopolitical security issues that we're hearing right about now in the news are also a factor in terms of having robust and resilient infrastructure. So this provides a perfect storm opportunity for distributed fiber optic sensing, for a once in a lifetime opportunity. So we have basically two categories that we should think about here as we deploy distributed fiber optic sensing. One is existing infrastructure where fiber already exists. Now, again, I'll provide the caveat here that the data is not out there right now. Ranges are available, and that's what I tried to provide you here in terms of how much fiber exists in a usable manner near some of our key infrastructure areas. Transmission is estimated to be maybe 25 to 40%. Substations, maybe 40 to 60%. Gas pipelines, 15 to 30. So the caveats here are, where is this fiber? Are there strands of fiber available? Are there fibers that we can utilize now that will give us the indication of the parameters and the use cases that you're going to hear about for distributed fiber optic sensing? If we have anything close to 175,000 to 275,000 miles available, these potentially could be used, whether they're fiber near the assets inherently or fiber through telecom overlays. These could be DFOS ready assets to be able to monitor our assets. Now, let's go to new infrastructure. That's a much simpler endeavor going forward. As we build out new infrastructure, we need to include fiber optics cable and conduit adjacent to new assets so we can use this. Why is that the case? Because if you look at the incremental cost of adding this capability to the cost of putting in the asset, we're talking on the range of only 1 to 3%. The ROI can provide a massive value with very negligible risk. So the best time to include distributed fiber optic sensing is now as you build. And again, try to look for those areas for retrofit. This is a hypothetical example. And the reason it's a hypothetical example is there aren't a lot of examples out there in the literature yet that people are talking about. I'm going to leave this with you at a very brief level, just so you see that the point of this slide is if you have a corridor, and here I've chosen a 100-kilometer corridor where a gas pipeline, a transmission electrical line, and telecom fiber is available. You need to look at the costs associated with implementing distributed fiber optic sensing, and you need to estimate the cost savings that should occur through each of these assets. What you'll see here are numbers that are reasonable. The cost of deploying the technology would be on the order of perhaps $300,000, and the cost of or the cost savings associated with each of these distinct utilities is also estimated here. The bottom line here is in this hypothetical business case, you're getting a payback in 3 to 5 years or less. It could be much sooner depending on the criticality of the route. So two takeaways I want to leave with you here. One, distributed fiber optic sensing can monitor all assets simultaneously in a right-of-way corridor. And I'm going to encourage each of you out there to look at building your own business case with real numbers from your own data. This is, again, illustrative, and your numbers will differ, but this should give you hopefully motivation that there's a lot of value to be captured out there using technology. A couple more slides here before I pass it on. Fiber Optic Sensing Association, if you're not familiar with it, you should look at it in detail, please. We have over 30 members. They're comprised of tech providers, fiber cable providers, end users, universities, consultants. It's a wonderful organization where we're driving the awareness in the industry. We're motivating folks to look at the business cases like I just described, and we're moving forward into standardization. We're now excited about adding end users to our portfolio of members. For example, Texas 811, a very active end user, and also a major telecom provider have just joined our organization. So we are the rallying point for scaling distributed fiber optic sensing. And I encourage you to look carefully at whether or not this could benefit your organization. I'm leaving you this slide so you can go back and reference it over time. This is a high-level capture of the amazing project you're going to hear about from Alex and Wissem coming up. The 2025 project of the year was the AP Sensing's Brouillard pipeline. Why was this so significant? This is an 800-kilometer pipeline across multiple countries. It had tremendous challenges: construction activity, agriculture, geohazards, multi-jurisdictional. The solution used multiple types of sensors, and it provided real-time excavation detection. It's one of the world's largest. It had this multi-function integration. It provides, in my opinion, and the opinion of many, which is why it won the award, it's not just a demonstration, it's an operational validation that this technology is ready for scale, and this provided a strategic energy security for Europe. So the caption on the bottom right, I believe wholeheartedly, Brouillard isn't just a case study, it's a blueprint for global distributed fiber optic sensing development. And then my final slide I'm going to leave you with here is the call to action. And this is a very important thing I would like you to go back to and look at a little bit more depth. What can we do to bring this technology forward and truly capture the value? I break it out into 3 categories of entities: the asset owners and the fiber providers, the technology providers, and the regulators and the policymakers. Briefly, the asset owners and fiber providers, work on your business case. Look at where your fiber is adjacent to your corridors. Engage with FOSA and determine how to maximize and leverage this technology for your own needs. Technology providers, if you're not already a member of FOSA, look at your business case. Build your reference customers, partner across the value chain, and think about how your technology integrates in a total solution package going forward to provide better safety and better economic value. And then actively, we're working with regulators and policymakers to bring this forward. So the opportunities now, I showed you a lot here, and I just want to leave you with one final thought, that it's up to us as an industry to make DFOS a standard practice and not an expensive afterthought. And now you're going to hear amazing information and detail from Alex and Wissem from AP Sensing, talking about a very exciting project that demonstrates a lot of the value I just described. So, Alex, I've turned over control to you.
Thank you. So I'm Alex Joode, head of pipelines and terminals from AP Sensing. We're gonna talk here just briefly about distributed fiber optic sensing in general and its application to pipeline. Many pipelines will have fiber optic cables deployed parallel to the pipeline for telecommunication purpose, bringing data from field instruments, for instance. These cables have multiple fibers, and distributed fiber optic sensing equipment, in this case, the DAS interrogator, transform one of the fibers into a sensing fiber, transforming the cable, the telecom cable, into a sensing cable. In addition to telecom cables, special cables can be used to monitor strain, enabling the monitoring of ground movement around pipelines. So how does it work? Here on the top right, you send a pulse of light and wait till this pulse of light reach the end of the fiber before you send another pulse of light. As this pulse of light travels through the fiber, it sends backscattered light to the interrogator. And on the bottom right, this backscatter light, when it comes back, bring information in three wavelengths: Brillouin, Raleigh, Brillouin, and Raman wavelengths. As this backscatter light reaches back the optical interrogator at different times, it is possible to obtain information about temperature, strain, and acoustic signal from each position of the fiber. With that, it's possible to use fiber optic sensing for a variety of applications and for pipelines in particular. These are pipeline leak detection, third-party monitoring, real-time peak tracking, monitoring of slow ground movement and landslides, flow assurance, detecting obstructions and restrictions of different kinds, slack flow conditioning monitoring, and temperature monitoring. Thermal insulation allows also the monitoring of under insulation corrosion condition and the progress of multi-phase slugs. So these are very powerful applications, and especially because the way fiber optic sensing delivers this information with very, very accurate location. With this amount of information, however, it is important to have software tools capable of interpreting data, especially acoustic signals. Acoustic signals are transient events that need quick recognition in similar way that your brain recognizes sounds and classifying the sound, for instance, of an angry dog as a threat. We use AI tools like neural networks and machine learning to classify the acoustic signals and patterns because there are a lot of activities generating strong acoustic signals near or on top of pipelines. For example, plowing or other agricultural activities shown here. Signals from traffic at road crossings and parallel to roads are another one. Oops. This technology has been extensively tested to recognize, for instance, the acoustic signals of leaks. We have conducted many tests, hundreds of tests, using gas bottles, methane gas bottles, using fiber optic cables at different distance, and also using air compressors, which performed leak trials in field conditions in using fiber optic cables of pipelines, which were monitored pipelines over 50 kilometers or more. And tests were done, different leak rates and so in different ground conditions and so on. Also, third-party interference is extensively field tested. We tested, it's approaching more than 1,000 field tests now, including drilling machines, hydraulic jackhammers, electric jackhammers, excavators of all different sizes and types, backhoes and augers, machines, different types of machines, explosions, construction works, even people of different size digging and different type of machinery. Here shows not a test. This is a real threat that was identified in Europe. So this farmer was installing a drain pipe, and he saw the marker of the pipeline, and he thought he was away from the marker, therefore away from the pipeline. But in fact, he was on top of the pipeline. And this alarm is sent to the monitoring agent. We went there and took a picture and caught them doing that. This is another example of a real threat monitored in the Middle East. You have the sound being recorded at about 7 kilometers of a hydraulic jackhammer shown there on the pipe, on the picture. They were about 2 to 3 meters off the pipe. The monitoring agency went there and detected the sound, which tallies very well with the sound that was recorded by the gas. So this technology, on top of leak detection, third-party interference, can also be used for detecting events that are occurring inside the pipeline. For instance, pig tracking. Once the pig travels through the pipe, it generates sounds. You will see this in more detail with the presentation from Wissem. And what the information the pig tracking brings is the real time, the position and the timestamp of that position, the velocity of the pig at each position, and the estimated time of arrival. Why do you need a real-time pig tracking? I can give a few examples of these reasons, but there is many other ones. Pigs change velocity, right? So if you use a traditional way to monitor pigs, you will have an estimated velocity, an estimated position calculated based on the flow velocity and the different recorded positions. But during this travel, there is a change in the slippage factor due to problems with the pig itself or different surface, waxing, presence of different types of liquids, depending on the fluid. If it is gas, it could be water or condensate. Also debris of all sorts. And also, as the pig goes up and down the hill, you have different velocities, or it goes on curves, it goes into crossings, up and down crossings. It can be stuck in protrusions left by pipeline theft, for instance, or during construction. Misalignments of the pipe itself can cause a slightly change of the velocity at that point. And change in flow velocity as well. As gas pipelines change pressure, the gas flow increases with lower pressure. So how does this work? Very briefly here, as shown here on the top right, the pig is traveling from right to left, and every time it's hitting a weld, it makes a sound. And that sound is recorded by the DAS, which works approximately if you have a microphone every 10 meters, and that sound is recorded locally, right? And the sound local sound is recorded and then transferred to the DAS. So the DAS, the fiber optic cable acts as a sensing cable, as an acoustic sensing cable, and the calculation of the peak velocity is done by the inclination of this line that you see here, where in this graph the vertical axis is the time and the horizontal axis is the position. In this case, the pig is moving from right to left, and the time is going from bottom to up. And now Wissem can start his presentation.
Yeah, thank you very much, Alex. Very nice talk by you and Paul. I'm really excited to walk you through the Brewer Pipeline monitoring project right now. And thank you, FOSA, for this opportunity and for the award. So in the next 15 minutes, I'm going to talk a little bit more about the Brewer project and show how DFOS can scale from individual installations to large-scale energy corridors. So let me move to the next slide. And let me give you here some geographical context to the project. So the acronym BRUA stands for Bulgaria, Romania, Hungary, Austria. And we're talking here about a strategic natural gas transmission corridor in Central and Southeastern Europe. And you've probably heard in the news now about the challenges around securing energy resources. And I think this project would strengthen the regional energy security in Europe by enabling access to additional gas resources, and in this case, from the Black Sea and the Caspian Sea. And in this presentation, we're going to talk about the red part, or the red line on the map that you can see here. So that's the Romanian part. So we're talking about 480 kilometers of pipeline corridor, plus the extension to the Black Sea. That's roughly 310 kilometers. So that's 800 kilometers of energy corridor. And when we're talking about pipeline risks, I think there is a simple idea. So let me move back. There is a simple idea, I think, that you need to remember what's known as the Rumsfeld matrix. So risks can be categorized typically into three types. So we're talking about the known knowns, the known unknowns, and the unknown unknowns. And third-party intrusion is definitely a known unknown. That means we know that these activities occur, but we don't know where and when. And I think you heard all the numbers from Paul before, and you can see that some TPI mistakes here can lead to major incidents, right? And this is exactly the type of risks that we would like to address in this project. So from these risks, clear requirements emerge, and the operator wanted here to have continuous monitoring of the whole energy corridor in Romania, including threat detection, like mechanical and manual excavation activities, plus gas leak detection. And in addition to that, precise indication of the event location, fiber break detection, multi-level alarm reporting, and integration of this system into the available data communication interfaces and with SCADA. And this is where the distributed acoustic sensing comes in, and you heard the whole explanation by Alex how this works. And if we focus a little bit more on the phase-based DAS system, so this is a technology that enables detection of third-party intrusion by listening, let's say, to the vibrations emitted by such kind of events, and it's complemented by distributed temperature gradient sensing for gas leak detection. So we know here when we have a pressurized gas in a pipeline and up on a leak, the Joule-Thomson effect kicks in. We have a huge temperature drop, which can be measured by the DTGS functionality of the phase-based DAS. And there is a very basic principle, and I think you have to know in this work, you either want to be part of the problem or part of the solution. And we at AP Sensing would definitely want to be part of the solution. And what we offered or what we deployed for this project is actually amazing. We're talking here about 10 DAS systems deployed for the Brewer section, plus 6 DAS systems for the Black Sea extension. We're talking about 16 racks in sum, covering 800 kilometers of corridor. So each of the DAS systems covers one of the segments of the pipeline, and altogether combined, that's actually a solid solution to monitor the whole corridor continuously. And this is actually where DFOS is going now. That's the direction we're going, scaling up projects. And this is one example out of many at AP Sensing where we're dealing with assets having lengths over 500 kilometers. So the pipeline itself is a typical high pressure natural gas pipeline. We're talking here about a design pressure of 63 bars, diameter of 32 inches. That's for the Brewer section. And for the Black Sea extension, we have 40 and 48 inches. So the fiber or the sensing cable is installed in a duct 30 centimeters away from the pipeline wall at 2 o'clock position. And you can imagine, so if we're talking here about a spatial resolution of 10 meters, that means over the entire corridor, we have 80,000 microphones listening to the vibrations around the pipeline, either it is TPI or gas leakage. Okay, so the project follows actually a very structured life cycle. So from the initiation to the engineering, implementation, then commissioning and final handover. But what's important here is that scaling is not only about the technology itself, but it's about also managing complexity, coordination, and stakeholder management, a lot of communication as well. And I would like to focus on 4 key stages in this project. That's factory acceptance testing, fiber to asset mapping, system configuration, and site acceptance testing. And before deployment, so the system is validated in factory conditions. So we delivered here the sensing equipment and the accessories to the rack integrator in Romania. So everything was integrated over there. And we tried to demonstrate all kind of capabilities of the test system during the factory acceptance tests with the EPC and the end customer. So we simulated a bunch of different acoustic signals. We made sure that the DAS is able to recognize these patterns. Also, all fiber break simulations at different positions, and we made sure that the system, or we demonstrated that the system is capable of measuring the data until that breakpoint. So this is actually a benefit also of the DAS. If you have fiber break, that the DAS is still able to measure until that point. And all of these notifications, alarms, details sent to the very simple operator interface. So for, let's say, the real world complexity starts. So it's all about risk management, making sure that all the systems configurations are worked fine before the installation on site. And whenever the substations were ready and the DAS systems, the racks, they were installed, secured in these substations, and then connected to the sensor fibers. So this is actually the first step which we made during the commissioning phase. And I believe this stage is what gave the distributed fiber optic sensing sense. Because if you don't do the fiber to asset mapping properly, you will end up having wrong or very bad event locations. So I can give you an example, like if you have a fire or a problem somewhere and then you call the firefighters and you give them the wrong address. So of course, it doesn't make any sense. So then they will be looking at a completely different location. So that's why we put actually huge effort in this task. We performed vibration tests at like 700 access points. We calculated the overall length in these manholes and tried to provide, let's say, the best position accuracy as possible for this project. And when we're talking about scaling a project, so we're talking also about dealing with real field conditions. So we're not in the lab anymore. So this is a full deployment. It's not pilot anymore. We're in the field. We were doing mapping in flooded areas, in sunflower fields, in corn fields. You see a very funny picture here. The plants that were even taller than a person. And again, so you have to understand, without proper mapping, even if you have the best sensing system, you cannot really deliver reliable event accuracy. So it's compulsory. It's very important to do such kind of tasks during commissioning. Okay, then later on, we did, and that's what we usually do, the system configuration. So all of this is done in three different layers. The first layer is the configuration of the different DAS systems. That's the optical channel settings, data storage, the AI models generation, configuration, the background noise learning, alarm parameter configuration. And then all of this information is implemented later on into the operator interface. It's very a user-friendly interface, which shows the map. So all of this fiber to asset mapping information is implemented in here for both by the Brewer part and the Black Sea extension. And then all of this information then is forwarded to the SCADA system using the IEC protocol. And you can see here that the notifications or alerts, they are not isolated anymore. So they are taken part of the operational workflow of the operator, of the end customer. During the handover, so we did the site acceptance testing. It was divided in two parts. The first part was the TPI detection. So here we made a real excavation activities along the pipeline at several locations. So to make sure that, or to demonstrate basically that that theory is working, and now in the field everything is working fine. We can see it in the waterfall diagram of that system, and Alex was showing actually a very nice example from another project. So here we can see in the waterfall diagram one of the excavation activities where the system is able to detect and classify these events and then send the corresponding information to the operator interface. And there is some bubble somewhere here on the map showing the location of the alert on all the information, timestamp, GPS coordinates, and so on. And the second part was the leak testing, or this is actually the tricky part or challenging part in most of the pipeline project. And in this case here, we used the functional test unit to stimulate the leak. That means we generated a leak-like acoustic signal. In addition to that, we generated a temperature drop, so similar to what happens, as I explained before, based on the Joule-Thomson effect, when a certain gas release occurs and you have temperature change. So in this FTU, it's possible to adjust all of these parameters and provide a certain pattern that's recognized by the DAS system as well. And if it's integrated with this operator platform, so you can see that somewhere bubble indicating the alarm and all of the information. And this information was transferred to SCADA, and the end customer was happy, and that was part of the handover. In addition to that, one of the, let's say, great capabilities of the DAS is big tracking. And you heard what Alex was talking about. Whenever there are some, let's say, debris or the pipeline has to be inspected or cleaned. So the operators, they send such kind of constructions, so pipeline inspection gauges into the pipe. So this is traveling through the pipe, and while it's traveling, it would generate like local pressure disturbances, which induce such kind of acoustic waves called sometimes negative pressure waves with velocities beyond 400 meters per second. And the pig itself, it has actually velocity of like around 3 meters per second. And when it's moving along the pipeline, so these two discs, they hit the girth welds, and then every like 12 meters in this case here, so the pipeline sections that were 12 meters long, you can hear to these banks. And I would like to share this audio with you so you can hear every 4 seconds these two banks of the two discs. So turn your volume up. Yeah, and I think that's amazing because we have a fiber here and a cable and a duct at 30 centimeters away from the pipeline. The pig is in the pipeline and it's just generating this acoustic, let's say, noise or signal when it's touching these welds. So I think it's fascinating. And I think that the audio shared by Alex was fascinating as well here. Okay, so still 2 slides to go. I shared with you how the pig sounds, and this is exactly how actually it looks like on the waterfall diagram when it's moving through the pipeline. So in this case here, during one of the campaigns, so the DAS system was able to recognize where the pig is, and it was classifying this pig correctly. These green bubbles, it's sending the information to the operator interface. And then you can see the pig moving along the pipeline on the map. The operator can see what is the pig position, the pig speed. And the main idea is whenever the pig gets stuck, then they can see, okay, what was the last position the pig was detected, and then they can intervene. And that's actually a very good demonstration of the pig tracking capability of the DAS system here. Okay, so this is one slide and then the conclusion. And I think this is a very nice story as well. During the commissioning, we just configured the DAS system, and the next day we had a bunch of fiber break alerts on the DAS waterfall. So we were a little bit shocked what's going on here. We informed the operator, so he sent a crew, and they found out that some rodents, they damaged the fiber optic cable. I don't know if they were very hungry and they thought, okay, that's a piece of spaghetti, or they were doing some dental care. Anyhow, they cut off the piece of cable, they spliced the cable, and then they sealed the cable entry, because that was actually the problem. So the company doing the cable installation, they forgot to seal the cable entry to the substations. And once they did that, and everything went fine at the end. So it's just another demonstration of how DAS, or demonstration of the additional value of the DAS in a different scenario. So finally, that's the conclusion before we move to the Q&A session. I'm sorry I took a little bit more time than I should. I think Brewa demonstrated here how DFOS can secure large-scale energy corridors. It offers monitoring with fast detection. It improves situational awareness. And just maybe ultimately what I would say here, so the 800 kilometers of pipeline is probably the worst place to play hide and seek, but not if you have a DFOS system. Yeah, so that's pretty much it from my side. I thank you very much. And then we can move to the Q&A session.
Thank you so much to our presenters today. We do have a few questions. If you didn't get a chance, on the bottom of your screen, you should see a Q&A. You're welcome to add any questions in there. And if we don't get to yours, we can try and reach out to you after this as well. So the first question I have is, what are the challenges associated with implementing DFOS over existing OPGW and ADSS fiber cables in power transmission networks?
You want to take that, Alex?
No, you can take it.
So this is a topic actually was a little bit different, which is a little bit different from the pipeline topic we're talking about today. So I believe the questioner is Mr. Adel Lilu is asking about overhead lines. And this is definitely an emerging topic at AP Sensing. I think I cannot disclose too much information here because it's a very, I would say, emerging topic, but definitely we can discuss it outside of this webinar.
Thank you so much. Okay, another question. With your own words, what has been the biggest operational benefit your clients have seen after implementing this system?
I think they're talking specifically about the AP sensing system, right?
I believe so.
With this project. Yes? No?
So can I see the question again?
Yeah. What has been the biggest operational benefit your clients have seen after implementing this system?
Well, if we're talking in general, that of course, so having the DAS system for any kind of asset monitoring. So if we're talking about pipelines or power cables, the DAS has a huge benefit of having a continuous monitoring of the acoustic around the asset. So if there is any excavation in the vicinity of the asset, then of course the operator will be informed at an early stage. So we're talking here about predictive detection and not reactive action. So most of the times, if the asset is not monitoring using a fiber and a damage occurs, then at the end, the operator has to go there and see what's going on. But with the DAS system, you're able to detect such kind of activities before the damage occurs, right? And there are different scenarios here. So we're talking about TPI. The same thing with leak detection. So whenever you have a leak, even a small leak, so you would be able to see it, right, or to hear it, to listen to it before it gets too late. So this is the general. Now, specifically for the Brua pipeline, we had at least 4 different additional values. So instead of patrolling, for example, the pipeline, 800 kilometers doing patrolling like every day, that's not doable. So having a fiber installed along the pipeline, so you can hear to what's going on around the pipeline without sending people every single day to see what's going on. And if you're having 800 kilometers, then you need to look a lot of teams, crews going through different terrain, and some terrain they're not even accessible. So that's additional value. Plus, we're saying the fiber break detection, we're having here a lot of landslides. We detected actually more than one fiber break, not only by the rodents, but we had some landslide, or the operator has some landslide issues. We detected the fiber break there. We were able to locate it. They were able to remedy, let's say, the fiber break immediately, plus the big tracking campaigns and so on.
Thank you. I think this question is for Paul. Does FOSA have a listing of DFOS service providers for agencies interested in raising awareness of the technology and are launching pilot installations?
Yeah, probably the easiest place to start would be to reach out to the leadership team. But if you look at our membership, when you say service providers, I'm going to use that term loosely. It could be the service of providing the technology, which I'm going to assume is the basis of the question here. You can see by looking at our membership at fiberopticsensing.org, we have a plethora of different providers of technology, and every one of those technology providers would be more than willing, I'm sure, depending on the application. They tend to specialize in different vertical markets to engage with you, to show you demonstrations, set it up. I mean, I don't want to speak too generally, but typically, bringing a unit out to your location, spending a few days to set it up, calibrate it, determine the GPS locations of your route, and then demonstrate to whomever you'd like to have see it how the technology works is fairly easy to do. So I would encourage whoever asked that question to reach out, depending on your vertical market. That's my answer, Catherine.
Thank you so much. Okay, the question
Great.
from a student doing research on master's degree in Kuala Lumpur. His research is on multi-stage denoising and its impact on feature extraction and classification in DAS signals. What is a main challenge when using denoising techniques in real critical environments like pipelines? Maybe Alex?
Yes, I think we will reach you and get these questions answered in a
Okay,
different forum. Yeah, it's
perfect. Thank you.
too technical.
Very
There's
good.
actually a very nice question now from Joseph Martin. Sorry, Catherine.
Yeah.
So what is the frequency resolution used by DAS in order to be able to reconstruct the audio signals with the DAS data? Very, very nice question. Actually, you have to know that the DAS is based on COTDR technique. That means you are usually limited to your fiber length. That means if you have, that's a rule of thumb, 10 kilometers of fiber, so you can have maximum 10 kilohertz of pulse rate. So that's 5 kilohertz bandwidth. So in this case, we had DAS systems with 50 kilometers and 70 kilometers of ranges. That means the maximum which we could have is actually 1 kilohertz or 2 kilohertz. That means all of this reconstructed audio was done with 1 kilohertz pulse rate. So that's just 500 hertz of bandwidth. And you have to know that these signatures, these signals, they are low frequency. So digging in the ground is low frequency. The pig traveling in the pipeline is low frequency. It's not like high frequency music or something. So it's detectable by the DAS, and the audio can deliver the exact signature what is actually going on in the ground or in the pipeline.
Thank you. Okay, I see another question from Chris McDade. Has anyone expressed interest in using this type of monitoring for natural gas infrastructure beyond the city gate to smaller distribution installations?
Yes, we are already looking at that with some clients doing tests and so on. We already installed in one application in Abu Dhabi, actually, a low pressure distribution network with 7 bar. It's already installed and tested.
Oh, perfect. Okay, we have a couple questions related to how the cables are located. The first one is, you mentioned the cable is located at 2 o'clock. Is it enough to have only one cable for leak detection? Have you tested leak detection, which occurs at 7 o'clock, opposite of the cable location?
Amazing question. Thank you, Dimitri Jibat, for that question. So if we're talking about low pressure gas pipelines, or in general low pressure pipelines, then definitely it's good to have additional fiber redundancy, especially if you're dealing with huge pipelines. And here we're talking also about the medium. So whenever we have gas, let's say release from the pipeline, so if it's going up, then it makes sense then to position the fiber at the higher hemisphere, or the upper hemisphere, so from 2 o'clock to 10 o'clock. And if we have fluid pipeline, so that's more the gravity effect, then you would place your fiber at 7 o'clock to 5 o'clock. So in this case, for the Brua pipeline, we have 60 bar. So that means it's in the case of leak, then the release would be tremendous, right? And just one fiber at the upper hemisphere is actually enough.
Well, thank you so much to all our speakers today, to Dr. Paul Dickinson, Dr. Alex Joode, and Dr. Wissem Sfar Zaoui. Appreciate everything. We learned so much. Thank you to everyone for your questions. If we didn't connect, we'll try to connect with you after this webinar. And thank you so much and have a great day, everyone.